So this is 2014, number 26. We're looking for the derivative of the integral from a constant to a function of 1 over 1 plus t squared dt. So in order to take the derivative of the integral, this is just the first part of the fundamental theorem of calculus. We can replace the t with root x, but then we have to multiply by the derivative of root x. So we end up with 1 over 1 plus x times 1 over 2 root x, which looks like that ought to be choice A. That's our fundamental theorem of calculus. Just plug in the upper limit. If the lower limit is a constant, plug in the plug in the upper limit as your t value into the original function there, and then multiply by the derivative of that upper limit. All right. Let's see here, 86, which was a calculator question. Did we do this one already?
Yeah, we did.
Okay, I was gonna say, I remember doing it, I just couldn't remember if it was in this class period or different class period. All right, we also got number 7 and number 10 from 2014. So let me go back here and see if we've done either of those yet. I don't think we did 7. I don't remember doing that in any of the classes. So let's throw that one up there. This is number 7. Oh, cool. I need to get my toolbar back again. Or else it's not going to let me write. Bear with me here. Every time I insert a clipping, it takes away my ability to write. For no apparent reason. All right, so we're looking for the limit as x approaches infinity of x cubed over e to the 3x. So for this one, there's 2 options. One, you plug in infinity, you recognize this is infinity over infinity. So first thing you can do is you can just look at it and say, well, which one of these things increases more rapidly as x goes towards infinity? And the answer to that is the denominator. An exponential always increases more quickly than a quadratic or a cubic or a polynomial function. So if the denominator is growing more quickly than the numerator, then that means we should be approaching 0. But we might also, if we don't remember that, you can also just use L'Hopital's rule, which gives you 3x squared over 3e to the 3x, which is still infinity over infinity. But then you can use it again to get 6x over 9e to the 3x, which is still infinity over infinity. But then you can use it again to get 6 over 27e to the 3x. And now we can see that we have 6 over infinity, which is definitely 0. Any questions there on 7? That makes sense to everybody? Okay. Did we do number 10? Oh, question?
No, I was just saying yep.
Ah, okay. Does this one look familiar to anybody? Number 10? I know I did it. I just don't know if I did it in this class or the other class.
Yeah, we did that one.
We did that one? Okay. Yeah, I see the 2013 test to take a look at now also. Number 20. I don't believe we did this one, but we should be able to now because we did one just a minute ago that was similar to it. Oh, cool, my toolbar disappeared again, and I can't go back to the pen. It's going really well today. All right, so number 20. For x greater than 0, the derivative of the integral from 0 to 2x of this thing should be, and so once again, this should just be the natural log of 2x cubed plus 1 times the derivative of 2x, which is just 2. So this should just come out to be 2 natural log 8x cubed plus 1. Choice D. Easy enough or no? Any questions there on that one?
I'm sorry, can you explain where the 2 in front of the natural log came from?
Yeah, so this is the integral from it's the derivative of the integral from a constant to a function. So whenever we have the derivative of an integral from a constant to a function, you always take that function, plug it in as the t value, and then take the derivative of that function. Because if it's just the derivative of the integral from a constant to x or to some variable, like if I just had 0 to x, derivative natural log t cubed plus 1, that dt should just be natural log x cubed plus 1 every time. And you just plug that in. That's the first part of the fundamental theorem of calculus. The derivative and the integral cancel each other out if it's just a derivative with respect to x and if it's a constant to just x. But as soon as it becomes something else, suppose we make this the derivative with respect to x of 0 to any function u of natural log of t cubed plus 1 dt. Then we have to do natural log of u cubed plus 1 times the derivative using the chain rule with respect to x of u. In our case, the u is a 2x, so the derivative of 2x is 2. That's why we get a 2 there.
Okay, thank you.
Yep, so like if this was 0 to sine x, you do sine x, you do natural log sine x cubed plus 1 times the derivative of sine x. You'd have a cosine x out in part of it, and so on.
Okay, thank you.
Yep. All right, 24. We got a function g, 4x cubed, 3x squared minus 6x plus 1. We want to find the absolute minimum on the closed interval. So since this is the absolute min and it's on a closed interval, we have to check critical values and we have to check endpoints. So first off, we'll look for any critical values to this. So g prime is 12x squared plus 6x minus 6. Or if I take a 6 out of that, 2x squared plus x minus 1. And we should be able to, I hope, factor that. Let's see, we'll need a plus 1 and a minus 1 there. And we end up with x equals a half and x equals negative 1. And so they have two critical values on this interval. So we're going to put negative 2. We're going to put negative 1, we're going to put a half, and we're going to put 1. And then we'll test values in between each of these intervals to see when the function is increasing or decreasing and determine where our absolute minimum might occur. So if we plug in something between negative 2 and negative 1, like negative 1.5, negative 1.5 times 2 minus 1 is still a negative, and then negative 1.5 plus 1 is still a negative, so this is positive. So we are increasing. And then between negative 1.5, like 0, we get positive times a negative times a positive, so negative, and we're decreasing. And then between a half and 1, like 3/4, we have a positive, and a positive, so we're increasing. So the only place we might have an absolute minimum is over here at negative 2, and here at 1/2. And so we just need to see if g of -2 or g of 1/2 is smaller. And this one's a max, so it couldn't be an absolute min. And this one, we're going up. So clearly we're going to be larger at 1 than we were at 1/2. But over at -2, we're going to be less than we were at -1. Everybody good so far with that? Hopefully. And then you just need to figure out what that is. So g of -2, let's see, that's -32. Plus 12 is -20. Plus another 12 is -8. Plus that one more is -7. And 1/2. If I plug in 1/2, we'll see here, this is already what? This is an 1/8. This is so 4 times an 1/8 is 1/2. Plus 3/4 minus 3 plus 1. This is definitely greater than -7. So it looks like our absolute min should be -7. Good or no?
Yeah, thank you.
Uh-huh. And then 28, let's see, the function is sine plus cosine. We want the point of inflection where it changes from concave down to concave up. So we'll take our derivative. F prime is cosine x minus sine x. Then we'll take our second derivative for concavity, negative sine x minus cosine x, and set that equal to 0. And so this gives us, negative sine x equals cosine x. That can only occur at increments of pi over 4 when sine and cosine have opposite signs. So in the first quadrant, sine and cosine have the same sign, so that won't work. Second quadrant, sine is positive and cosine is negative, so that'll work. So x equals 3 pi over 4. And then the third quadrant, they are both negative values, so that doesn't work. And then the fourth quadrant, this should be positive and this should be negative, which will make them work. So that's 7 pi over 4. And so we will put those two values on a sign chart here and plug in values on either side. We want to know when it goes from concave down to concave up. So let's just test in the middle here. We could test pi. Sine of pi is 0 minus the cosine of pi. So cosine of pi is -1. So we got minus -1 is +1. So we're positive. So we should be going from concave down to concave up, probably here at 3 pi over 4. But we'll plug in something less than 3 pi over 4, like 0 into that. That's still 0. And then cosine of 0 is 1. So we have 0 minus 1 is negative. So it would appear that we're going from concave down to concave up at 3 pi over 4. Any
Yeah, so I was just kind of confused on this question just because with the intervals that like we were given, because it was a closed interval from 0 to 2 pi. And so then between 0 and 3 pi over 4, like cosine of x would be positive until it reaches pi over 2 and then it becomes negative. So I was kind of confused because it increases and decreases like within the same interval.
Right. I mean, the cosine, yeah, I mean, cosine does, but whether cosine is increasing or decreasing, it doesn't affect what the concavity is. I mean, the concavity only is affected by what the sine of this whole thing is doing.
Okay, so I can just plug in any point regardless of like the changing quadrant and everything.
Yeah, yeah, exactly. I mean, so you'd note that, I mean, there's another value over here at negative pi over 4, right? So like negative pi over 4 is the same as 7 pi over 4. So you wouldn't want to plug in something below negative pi over 4. That would screw you up. You got to plug in something that's greater than negative pi over 4. So you'd have to plug in something greater than 0 for, for this value, because really our interval is only 0 to 2 pi.
Okay.
But
Thank
yeah,
you.
anything between 0 and 3 pi over 4, no matter what you plug in between that interval, this will come out to be negative. Even though cosine and sine, change signs within there and all that, or cosine changes signs between 0 and 3 pi over 4 at pi over 2. That doesn't matter. What matters is, does this whole thing change signs?
Okay, got it. Thank you.
All right, next one here, we've got a function whose first derivative is f prime of x is all this nonsense. How many relative extrema does f have on the open interval, negative 4 to 2? Okay, so we would need to graph this function in order to figure this out. So let's graph it. What do we have here? We have 3 minus 2x minus x squared. Three minus 2x minus x squared. And what was the other part of it? It was sine of 2x minus 3. And we want to know how many relative extrema does this have? What did it say on the interval from where to where? Negative 4 to 2. So on your graphing calculator, you can just change the window so you're only looking at negative 4 to 2. That's what I'm going to do here. Just going to have it graph only negative 4 to 2. So any relative extrema would be any place where this thing changes signs, right? If the derivative, because this is the derivative, if the derivative goes from negative to positive or positive to negative, that's going to tell us that the function itself goes from increasing to decreasing or decreasing to increasing, and that's when it'll have a relative extrema. So it looks like there are 1, 2, 3, 4, 5, 6 places where the derivative changes signs. So that would tell us that there are 6 places where this has a relative extrema. Does that make sense for everybody or no? All right, and then 92 here, we got the function f is defined for all x on this closed interval a to b, but f does not attain a maximum on a to b, which must be true. Well, according to the extreme value theorem, if f is continuous on a closed interval from a to b, there must be an absolute max and absolute min on a to b. And we have said that it is defined for all x in a to b, but not that it's continuous on all x from a to b. And it does not attain a max, so therefore it must not be continuous on that interval from a to b. Because if it was, it would be guaranteed to contain that max. Could easily draw a picture where it doesn't have a max, like here's a, here's b, here's our value at a, and there's our value at b. So it's defined for everything from a to b, but it's not continuous, specifically not continuous at b, and there is no absolute max on that interval, because as I approach this value that's, whatever this value or this hole is, I get closer and closer and closer to that y value, but I never actually hit it. There's no largest value that we obtain. So there's a sketch of what this graph could look like. Does that make sense to everybody? Okay, Krista, you said 14 yet? Is that 14 from the 2013 test that you're asking about?
Yeah, sorry.
Let's see here. I don't know if we've done it. We can find out. I don't know if we do this one. I remember doing this one in one of the class periods, but I don't know if it was this period. Either way, we can do it right now. So we've got this function f of x equals x plus b and ax squared if x is greater than 1. And so we want to find all values of a and b for which f is differentiable at x equals 1. Well, if f is going to be differentiable, it also has to be continuous. So we need the function f to be continuous at 1, and we need the function f to be differentiable at 1, which if it's going to be continuous at 1, the limit from the left has to equal the limit from the right. So we need to say the limit as x approaches 1 from the left of f of x needs to equal the limit as x approaches 1 from the right of f of x. The limit as we approach 1 from the left of f of x is 1 plus b. And the limit as x approaches 1 from the right of f of x is 1 times a, so a. If it's going to be differentiable, so if we want it to be differentiable at x equals 1, then that tells us that the limit as we approach f prime from the left needs to be 1. Needs to be equal to the limit as we approach 1 from the right of f prime. So we'll say f prime is just, f prime is literally just 1 if x is less than or equal to 1, and it is equal to 2ax if x is greater than 1. So we need to, at 1, set those equal to each other. 1 equals 2a. So a would be 1/2. And if a is a half, then that tells us that b should be negative a half, just by plugging it in up here. Does that make sense or no?
Yeah, thank you.
Anybody have any questions?
Can you explain where you got the 1 plus b equals a?
That's the limit as x approaches 1 from the left is 1 plus b. Right, if the function is x plus b, as x approaches 1 from the left, that's 1 plus b. And the limit as x approaches 1 from the right of f of x, I just plugged in 1 for x on the bottom piece from the right part of 1. So that's a times 1 squared, or just a.
Thank you.
When you, why didn't you go 1 equals 2ax? Why'd you just drop the x?
Not because this has to be true. This has to be differentiable when x equals 1.
Okay.
So it's 2a times 1, which is just 2a. That makes sense?
Yeah.
All right. We got number 84 from the 2014 test. All right. So 84 from 2014. We got this nice little graph with regions A, B, and C. It crosses through the x-axis there at 8. And it gives us the areas of these regions. So this one's area is 14, this one's area is 16, and this one's area is 50. And we want to know the average value of f on the interval from 0 to 8. Well, the average value of f from 0 to 8 ought to be 1 over 8 minus 0 times the integral from 0 to 8 of f of x. Well, this is the function f of x. The integral of it ought to be all the areas between the curves summed together. But remember that the integral, when we take something above the x-axis, is positive. But if the integral is something below the x-axis, that's negative. So 14 minus 16 plus the 50. Looks like that's negative 2 plus 50 is 48. 48 over 8 ought to be 6. Any questions there on that one?
Nope.
All right. Anybody have any, that's the last one somebody's asked for. Anybody have any other questions?